Hi there, welcome to the second lecture video of the linear regression section of the SMLC course. In this video, we're now going to learn about ordinary least squares, or OLS for short. Let's first start off with understanding what exactly ordinary least squares means and what it is. So OLS is the statistical method that produces the one straight line of best fit that minimizes the total squared error. This is a brief general definition of it, and it has a lot of moving parts and complex terminology, so let's break it down. The main idea of OLS is that it's a method that fits or trains our line of best fit to our data. It's what calculates the line. And the goal of OLS is to calculate a line that minimizes the distances between our predicted and observed values. This distance, is called the residual, or the loss, or the error. All those terms can be used interchangeably as well. But the main idea here is that if we look at this bottom right figure, this white straight line is called the residual or the loss. And what OLS is trying to do is that it's trying to calculate a line such that all these vertical white lines can be as small as possible, so that our linear regression line of best fit algorithm can be optimized to its fullest capability. And now that we understand the main idea behind OLS, let's get more specific into the math and how it's functioning. So OLS regression or linear regression, both terms can be used interchangeably, is fitted by minimizing the sum of the squares of the residuals. If we look at this top right image here, this is the formula for SSE, which stands for the sum of the squares, or the sum of the squared error. And error, like I said, is the same as residual. And if we look at this formula here, right, this symbol here is called sigma, and it represents summation. And what we're trying to do is we're trying to sum the squares of every single residual. So this difference, the difference between the predicted value and the actual value, that's going to be our error or residual. And what we're trying to do here, we're trying to square that, and we're trying to add all the squares of all the differences. We're trying to add the squares of all these differences to get the SSE value. And what OLS regression is trying to do is it's trying to get the smallest SSE value possible. There's more complex math behind it to find the most small sum of squares of the residuals, and I'm not going to go too in depth with that, but I want you to understand that the main idea here is that OLS is trying to find the most minimal sum of squares of the residuals. The reason why we square the data points is because the reason why we're trying to square the residuals when calculating the SSE is because some of the data points are below and above the line. If we look at this bottom right figure again, here we can see this data point here is above our line of best fit. So that means the difference between the observed and the predicted value is going to be positive. But here we can see that the observed value, or this data point, is underneath, it's underneath the line of best fit. So that means the difference between the observed and the expected or the predicted value is going to be negative. So since all of these residuals have different signs, to standardize everything and just obtain the magnitude of the difference, we're going to square the residual. So what I covered before is just the overall idea and understanding of OLS. There's some more complex math behind it, and if you want to understand that math to see how exactly OLS is getting the smallest sum of all the residuals squared, you can look at this YouTube video here. It does a great job of reviewing what OLS is, and it goes in depth with all that complex math. So now that we understand what OLS is, let's see the advantages of using it for linear regression. So one very important advantage of OLS regression is that the algorithm is best to use when you know there is an inherent linear relationship between your independent and dependent variables. So to explain that, the linear relationship, for example, can be, if we take for example our ice cream example from the previous video, right? If one of our features is going to be temperature, then we can say as the temperature of our location is increasing, the price of ice cream is also increasing. That is a linear relationship. It's an upward linear relationship, right? And this is actually going to be very good for a linear regression model, because since our data is linear and our algorithm is also a line of best fit, it's gonna adjust and fit perfectly with the data points. And as a result, if we use linear regression as the algorithm when we have our data being in a very linear relationship, then there's going to be less complexity compared to using other machine learning algorithms. So that's the main advantage of using OLS regression. It's when you know that your data has an inherent linear relationship. The next advantage is that if we use linear regression, it's very easy to implement and interpret. And we're going to see this in the next video on using Python to implement the linear regression model. Furthermore, an important advantage to be aware of is that you can obtain good predictions and results with linear regression even when you have a relatively small data set. And this is good because sometimes your data sets won't always be large, substantial, and filled with useful, detailed features. So even if you have a smaller data set, you can still train an effective linear regression model. And that's always good to have. So now that we understand the main advantages, let's now understand the limits and disadvantages of using OLS to calculate our line of best fit for the linear regression model. One thing to note is that if we use OLS for linear regression, in general, if you use linear regression, it's going to be limited to linear relationships. And by its nature, linear regression only looks at the linear relationships between independent and dependent variables because it's developing a line of best fit. So this is good, like I said before, it's going to be good if your data is already inherently linear, and that means your model can well fit itself to your data. It can train well with your data since it's already linear. However, linear regression always assumes that there's going to be a straight relationship between them due to the line of best fit, which can sometimes be incorrect. For instance, sometimes the relationship between your independent and dependent variables can be curved in nature or inherently nonlinear. Ultimately, this means that using linear regression can sometimes lead to an oversimplification if your data isn't inherently linear. And another important disadvantage to be aware of is that linear regression is especially sensitive to outliers, since we are squaring the residuals when calculating the line of best fit. And outliers can have a huge effect on the regression performance because they can skew the line of best fit, and skewing means that it can tilt the line of best fit into a direction which will make it not very optimal when making predictions when faced with new data. And this means that the line of best fit can be prone to more outliers, noise, and it can overfit on your data, which is something we definitely do not want to have in our machine learning models. Furthermore, another problem with linear regression is that since linear regression is based, not really a problem, it's more so a limitation. Since linear regression is based on a line of best fit, it's only looking at the relationship between the mean of the dependent variables and the independent variables. When I mean mean, I mean that linear regression is completely based on a line of best fit, and a line of best fit is inherently an average. It's an average of all your training data, and it's making predictions based on that average. And this kind of ties back to what I was talking about with Francis Galton. Remember how I mentioned that his founding of the idea of regression is that it's a deviation or moving towards the average of the entire population. In this case, linear regression is based on a line of best fit, which is an average of all your data points to develop that line of best fit. And just as the mean is not a complete description of a single variable, linear regression is not a complete description of relationships among your independent and dependent variables. And the final main disadvantage that I want you guys to be aware of is that when using linear regression, it can be prone to multicollinearity or redundancy between your independent variables. What multicollinearity means is that there are high correlations between two or more of your independent variables or features. This redundancy or high correlation, but when I mean high correlation, it basically means that your independent variables and features are very similar to each other. They're not providing new data for your model to learn from. So this redundancy between your independent variables can lead to a misinterpretation when the model is making predictions, and it can skew the model's results as well. Furthermore, the redundancy is not introducing any new valuable information that the model can learn from to perform better when faced with the complexities of newer data that it's not been trained on, right? The test data. And this redundancy also makes it difficult to understand and differentiate the individual impacts and effects of one feature on the target variable and the effects of the other redundant feature on the target variable, since both of those features are so similar and highly correlated. This essentially means that it will be difficult to determine which features will be most beneficial to help our model learn properly from the data and make accurate predictions on new test data. And that was a lecture on OLS. In the next lecture, we'll be using scikit-learn and Python to implement a linear regression model, and we'll be training our model with the real Boston house prices dataset. Thanks everyone, and I'll see you in the next lecture.